So we now return to the question of what is it that is new in today's cloud infrastructures that distinguishes clouds from previous generations of distributed computing systems. And essentially there are four major characteristics that distinguish today's clouds and the problems that they raise that are different from previous generations of distributed computing systems and problems. They are massive scale, on-demand access, data-intensive nature, and new cloud programming paradigms. I'll say a little bit about each of these now, but then we'll flesh these 4 points out over this lecture as well as the next few lectures. Massive scale essentially means that data centers are very large. They contain tens of thousands, sometimes hundreds of thousands of servers, and you could run your computation across as many servers as you want and as many servers as your application will scale. On-demand access means that you don't sign a contract to purchase resources up front. There is no upfront commitment. You only pay for what you use, and anyone can do so. You could use it, your family, your mom, your grandmom, anyone could use it. The third aspect is data-intensive nature. What used to be megabytes has become terabytes of data. What used to be petabytes has now become exabytes of data. This is data that needs to be stored, and it needs to be processed, and perhaps it needs to be served up in real time. The data might include daily logs of what's going on at certain web services. It might include forensics, it might include web data, it might include a whole lot of other data. And when we talk of large data such as terabytes, petabytes, exabytes, humans have what is known as data numbness. Just like number numbness, we are often unable to tell how large data sets are. For instance, we consider Wikipedia to be a very large data set, but you can compress Wikipedia into just about 10 gigabytes. So Wikipedia by itself does not count as big data or as data intensive, but yet there are data sets out there that are much, much larger and measured in petabytes and exabytes. Finally, there are new cloud programming paradigms that have made it easier to process such large amounts of data. This includes MapReduce or its open source implementation Hadoop, as well as storage engines which allow us to store this data and query it fairly efficiently. This includes key value stores such as Cassandra and NoSQL stores such as MongoDB, which you'll see later on in the course. These new programming paradigms and storage paradigms are very accessible. They are easy to program and easy to configure, and many of these systems are open source. So essentially what I'm saying is that if someone gives you a problem and says, hey, here's a cloud computing problem, you may want to test whether or not that problem has at least one of these four aspects that are listed on the slide. If it has at least one of these aspects, it's very likely to be a new cloud computing problem. If it is missing all of these four aspects, then it's possible that it's a problem that is already well known and that has well known solutions. So it should give you pause. So the first important aspect of cloud computing is massive scale. Facebook, for instance, today, or at least in 2012, ran about 180,000 servers, and it had exponentially grown the number of servers from 30,000 in 2009 to 60,000 in 2010 to its current number. Microsoft in 2008 was running 150,000 machines, out of which 80,000 were running Bing, their search engine, and they were growing at that point of time 10,000 machines per month. You can imagine where that size is today. Yahoo in 2009 was running 100,000 machines in the data centers, and these are split into clusters of 4,000 because of the way Hadoop runs. Amazon Web Services was running 40K machines in 2009 with about 8 cores per machine, and of course this has grown by now. eBay and HP were also running a lot of machines across many data centers, and Google, the number is not known, but it is widely reputed that it is running one of the largest collections of machines anywhere in the world. So what does a data center look like from inside? So we'll take a virtual walk through a data center. This is just to give you an idea of what a data center warehouse actually looks like. And there are many links for you to see, and I'm going to have the links up here on the slides themselves so that you can go and either read them up, or I'll have a few YouTube videos that you can also look at. So the main room in a data center is, of course, the servers. They don't look very different from the front or from the back. They're just regular machines, except that these might be rack-mounted machines. Inside, they look just like your regular desktops or workstations or laptops. However, some of them might be highly secure. For instance, they might be behind walls. If they're storing financial information, that is highly sensitive. Where does the power come for these servers and the switches? Well, a lot of the power comes from offsite, such as hydroelectric power or coal power, which even today is the predominant source of power for data centers. Some data centers have solar panels, which provide for some small fraction of the data center's power usage. In many cases, for instance, solar panels might be used to power the lights inside the data center. However, there is a couple of important metrics that are used to measure the efficiency of the data centers in terms of water usage and power usage. These are known as water usage efficiency, or WUE, and power usage efficiency, or PUE. The water usage efficiency is essentially the annual water usage divided by IT equipment energy in liter per kilowatt hour. A lower number here is good, which means that you're using less water per energy that you're using. PUE is total facility power divided by IT equipment power. Again, here a lower number is good because essentially this means that you're using a larger percentage of your incoming power for powering your servers and your routers and switches. For instance, Google has one of the lowest PUEs in the world. It's about 1.11. You can never get to a PUE below 1, obviously, because you can't use more than 100% of your power. Now, when you have power, you have servers, you have heat, and so you have to cool these servers. So you might suck in air, maybe from the top. Then you need to purify water and spray the water into the air. And then there are motors per server bank that are spraying the air into the servers themselves to then cool the servers. This is just one of the different cooling infrastructures you may have. Other data centers may use completely different cooling infrastructures than the one that I have described on this slide. There's a couple of fun videos to watch as well, including a Microsoft GFS data center tour, as well as a time lapse of a data center construction of a Fortune 500 firm. Both these are available on YouTube.